Hi, in this video we want to look at Young and Freedman's Chapter 10, Section 3, which now combines both rotation and translation, where translation is straight line motion, basically. So things are just getting more and more complicated, combining earlier concepts the further we go into the book. So let's start with adding up kinetic energy of something. So you might remember from earlier chapters, the kinetic energy equation for translation is fairly simple. It equals 1/2 mv squared, where v is the velocity of whatever is being translated or whatever is moving. Now, this still applies to something that is rotating if it's moving in a straight line. So we think of that object in terms of its center of mass. If you take its mass and you somehow equated its mass to a point, we call that the center of mass. And so we would apply this equation to the translational movement of a center of mass of something that's spinning or something that's rolling. So that's fairly straightforward to find the kinetic energy of something that's rolling or spinning. We simply have to know where its center of mass is and you know what direction it's moving in. We don't even necessarily have to know what direction it's moving in to calculate the kinetic energy. So that's fairly straightforward, 1/2 mv squared. Now, what about the kinetic energy of rotation? We learned about it in the previous chapter, in Chapter 9, basically that the kinetic energy of something that's rotating or rolling or spinning is 1/2 the moment of inertia times the angular velocity squared. So 1/2 I omega squared. You'll remember that the moment of inertia varies from type of object to type of object. There's a nice little chapter or chart in Chapter 9 that tells you some of the equations for various moments of inertia. Angular velocity is the velocity in radians of a point on the outside of whatever is rotating. And so basically, to find the total kinetic energy of a rigid rotating body moving in a straight line, you're just going to add these two equations together. So you're going to have 1/2 mv squared for the translation kinetic energy, and you're going to add that to 1/2 I omega squared for the rotational kinetic energy, and there you have it, just simple addition. Notice we're talking about a rigid rotating body. We'll get to the complication of an elastic body in Chapter 11. Okay, so there you have the total kinetic energy of something that is both moving and rotating. Rolling without slipping means that if something is touching the ground, that there is no energy loss from the contact with the ground. And so let's say you have a perfect circle that's rolling without any slipping. In this case, then the velocity of the wheel's center of mass in terms of the bottom is going to cancel out the velocity of the point at the very bottom. So this point at the very bottom of a wheel that's rotating and rolling is going to be, in effect, a net zero. Let's say you have a circular that's rolling in this direction. So it's going like this. Then at the bottom of the circle, it's going this direction at the same velocity that the wheel is going this direction. So those two vectors, as it were, cancel out, so that the net velocity of the point at the bottom of the circle is zero. Now at the top of the circle, it's going to be rotating at the same velocity as the center of mass. So there, at the top, you're going to have double. The point at the top of the wheel is going to have double the velocity in this direction. So the point at the bottom of the wheel, touching the ground, has a net zero velocity. But the point at the top of the wheel is going to have, in effect, a double velocity. So the velocity of the center of mass in the center is just one of the velocities. And so using an equation from Chapter 9, Section 3, the velocity of the center of mass is simply going to be the radius times the angular velocity. That's in radians again, where the angular velocity omega is the angular velocity in radians per whatever going around. Okay, so there's an equation that may be of some value to know for a circle that is a wheel that is rolling without any slippage against the ground. Okay, so then this is a very long section. He then gets into, they then get into the dynamics, that is the forces that might combine between the forces of translation and the forces involved with torque in rotation. So we're going to have two different equations here for the relationships between force and motion. So as far as the translation is concerned, we have good old Newton's second law from earlier chapters, force equals mass times acceleration. There you have it. Then we have what we had in the previous section in 10.2, that the sum of the torque forces is going to equal the moment of inertia times the angular acceleration. Not the A is the translational acceleration. The alpha here is the angular acceleration. What's the value of these? Well, two of the examples that Young and Freedman give, one involves a yo-yo, one involves a bowling ball, and he doesn't use any actual numbers. He uses letters, variables, and derives some equations, for example, for how to find the velocity of a yo-yo or the velocity of a bowling ball at a particular point in time. So having these two equations may give you the possibility of solving some various things because, you know, if you have an equation in two variables, then you need two equations to be able to solve something. So having these two equations can be helpful to solve various other things. But those are the two equations for the forces, the dynamics involved with, first, the translation of a body, and second, the rotation of body. I might add that the angular acceleration, alpha here, is a, using the right-hand rule, it's a z vector. Remember, from the first part of this chapter on torque, 10.1. So it's pointing, you know, if it's rolling this way, it's pointing toward me. If it's rolling this way, then it's pointing into the screen. So there's a section there where he derives some equations. Both of these equations work only if there's an axis through the center of mass, and that axis, if that axis is a axis of symmetry, that's important. And then if that axis is not changing directions, then these two equations can be connected to each other, as he does in the examples. I know that's somewhat abstract, but in some of the problems, you can see how this can be used practically. The final section, kind of at the end of this big section, he talks about rolling friction. That's, of course, where there is some loss of mechanical energy or loss of heat in the contact between the rolling circle and the ground. So if the surface or the circle is somewhat deformed or deformable, maybe it's a car tire with a deformity, or the ground has a bump in it, then there's going to be some mechanical energy that is lost. And the normal force, that is the force pushing up from the ground, as it were, is going to produce a torque in the opposite direction that's going to oppose rotation. And so you'll have to take that into account. The formulas won't work quite so neatly.